If an inert gas is introduced into a reaction container, will the equilibrium shift? Many people might instinctively think, yes, because the pressure changes. But the real answer is, not necessarily. It depends on a key condition, which you may not fully understand. Next, I will use an interactive simulation experiment to help you thoroughly grasp this issue. This is a reaction chamber with a piston, inside which a classic reversible reaction takes place, the conversion between nitrogen dioxide and dinitrogen tetroxide. The dark reddish-brown color represents nitrogen dioxide, while the lighter color represents dinitrogen tetroxide. The color inside the reaction chamber intuitively reflects the ratio between the two. There is a key variable here, the piston. When the piston is locked, the volume is fixed, meaning constant volume conditions. When the piston is free, the volume can change freely with pressure, meaning constant pressure conditions. Next, under these two conditions, assuming constant temperature, we will introduce an inert gas argon into the equilibrium system and observe what happens. First, under constant temperature and constant volume conditions, that is to say, with the piston locked. After the reaction reaches equilibrium, we add argon to the system. At this point, the color shows almost no change, and the equilibrium does not shift. Why? Because under constant volume conditions, although the total pressure indeed increases, the key point is that the concentrations of dinitrogen tetroxide and nitrogen dioxide do not change, and their partial pressures remain unchanged. If the partial pressures remain unchanged, the equilibrium will not shift. Now, let's switch the piston to free mode, that is to say, under constant temperature and constant pressure conditions. After the reaction reaches equilibrium, we similarly add argon. At this point, the piston is pushed upward and the volume expands. The color change is also interesting. It first becomes lighter and then gradually darkens again. Why is this? Under constant pressure, adding an inert gas forces the system to expand in order to maintain the same total pressure. As the volume increases, the concentrations of all gases are diluted, naturally causing the color to lighten and the partial pressures decrease accordingly. This is equivalent to reducing the pressure on the reaction system. According to Le Chatelier's principle, the equilibrium will shift in the direction that resists this change, that is, toward the direction that increases the number of gas molecules, trying to compensate for the pressure change. For the conversion between nitrogen dioxide and dinitrogen tetroxide, shifting the equilibrium toward the production of nitrogen dioxide increases the number of molecules, so the color darkens again. The shift in chemical equilibrium is essentially the system's response to changes in partial pressure. Remember the core logic here. Under constant temperature and constant volume conditions, adding an inert gas does not change the partial pressure, so the equilibrium does not shift. Under constant temperature and constant pressure conditions, adding an inert gas causes volume expansion, which lowers the partial pressure, shifting the equilibrium toward the direction that increases the number of gas molecules. Next time you encounter such a problem, don't just memorize it, think about whether the partial pressure changes and the answer will naturally come to you.